Good morning, everyone. I hope I'm audible to the people who are joined from Pune and Thiruvananthapuram.
Yes, sir.
Okay, and I hope my screen is also visible.
Yes, sir, visible.
Excellent. So let's start with questions from Pune. Puneet, any questions?
No, sir.
Okay. Any questions from Thiruvananthapuram?
No, sir.
Okay, who all have joined? Let me quickly check. Anjali, any questions? I guess Deep Ram is not around. Yeah, Anjali, any questions?
No, sir.
Okay, all right. Any questions from Bhopal? Any doubts, clarifications? Yes. Between omega and omega naught. We will come to that today when we go across the topic. Omega naught is the Larmor precision frequency. Okay, and that's given for a given spin. It's a constant by minus gamma b naught, given as minus gamma b naught. On the other hand, slowly you will realize omega will now take different shapes based on the pulse that you apply and what are the residual effects that you can imagine omega as the effective angular momentum. But remember, you're only looking at omega naught at equilibrium when the spins are precessing about B naught. It is an angular frequency. Yeah. Okay. Any other questions? Rishiraj, move to the center. I didn't want to record it, but now it will be online for everybody to listen on YouTube. Okay. Good. So if there are no further questions, let me continue from wherever I left off. So we were, once again, let me go back to whatever we discussed. For I not equal to 0, you have a non-zero mu. Once you have a given mu that interacts with a magnetic field, you would be able to have non-degenerate energy levels, therefore non-equal populations, and hence you can end up using that to do spectroscopy. And for NMR, generally we tend to focus on spin half systems where the allowed MI values are plus minus half, and therefore there is a two-level system when suspended in B naught will come up with an energy difference of gamma H cross B naught with the omega naught Lama precision frequency of gamma B naught. You'll see today that we'll introduce a negative sign here, but we will see that as we go. But overall, the energy difference is given by this, and we also said that the spins are quantum spins, quantum magnets, and therefore they are quite different from classical magnets where their orientation with respect to the B naught is going to be at an angle. Meaning, if you have a certain set of Cartesian coordinate system, alpha spins will be at an angle, beta spins will be at an angle with respect to B naught. This is something that we have seen thus far. And we said when you have an ensemble of spins, you're going to have a lot more. When you have an ensemble of spins, you're going to have a lot more set of alpha states that are going to be present, which forms a bouquet of spins there. Beta state, similar thing will be present. And you will resolve each vector into its mutually orthogonal components, where you would end up realizing for every vector, the transverse component destructively interferes, while the longitudinal component adds up, giving a magnetization for alpha and a magnetization for beta based on their equilibrium populations, which will once again interfere to give a small magnetization, which we call as a bulk magnetization that arises from the sample. Then we were trying to say, if you have the bulk magnetization, if you want to measure a signal, you cannot easily measure it when it's along V naught, and therefore we disturb it with a radio frequency pulse, get it to the transverse plane, and therefore measure it with a coil that is being present, where this magnetization cuts the coil to induce a time domain signal, which when you Fourier transform will give you a frequency domain spectrum. So this is where we left it off. And we were also trying to highlight a few things where when you have a chemical entity that you're trying to measure with NMR, you would be able to get the chemical shifts for similar chemical entities. For instance, the same methylene group, depending upon what it's bonded to, will give different chemical shifts, and we define the chemical shift as a relative energy unit, where omega naught is going to be minus gamma B naught. We'll see that as we go. No, it is not. Largely because you're going to have, in some ways, you are taking the B naught component out of it. Each of this will have a B naught. Yeah, and therefore ratio will factor it out, right? And the major reason 10 power 6 comes up is that both will be in magnitude of megahertz. Well, this will also be in megahertz. Subtracting a megahertz will take it to a few kilohertz. Therefore, you want to make sure you take the 10 power 6 component. Therefore, it gets a unit of ppm. Okay. So now that being done, we were also trying to understand how do multiple chemical shifts come, given that the electronic environments are different. Each has its own bulk magnetization. Therefore, for an example like ethanol, you're going to get 3 well-resolved chemical shifts whose integral is based on whatever number of protons are being present. And we were also trying to quickly highlight what the line width would depend on. There are further features that will come up here, which we will discuss maybe later this week. But for now, we can assume that a low resolution NMR will give you 3 lines without any hyperfine splitting. And the integral will go with the number of protons that are being present. That changes the total bulk magnetization for each system. And given that the shielding for OH proton versus the methylene proton and the methyl proton are quite different, their chemical environments are different. Therefore, you're going to get different chemical shifts. You could have had a scenario where you get OH CH3 and then CH2. I'm not highlighting to that extent because we are still talking in relative terms. I'm not writing any chemical shift, if you realize. Just trying to say 3 resonances come up. Just to highlight a little bit more on the R2, which matters a lot for solution state NMR spectroscopy. R2 is 1 over T2, where T2 we have learnt earlier is the transverse relaxation rate or the spin-spin relaxation rate. Relaxation time if it's T2. This is the same thing, but it's a rate. 1 over time will be a rate. And it's important to focus on this because this R2 is proportional to something called tau C. What is tau C? Isotropic tumbling times. What is isotropic tumbling time? It's the amount of time a molecule takes itself to reorient after every possible orientation and solution. Let me repeat again. Isotropic tumbling time is the total time taken by the molecule to reorient itself after having sampled every possible orientation. What do I mean by this? Let's say you take ethanol molecule and when it's in solution, remember it is not bound to any specific orientation in solution. Unlike a crystalline single crystal, where all the molecules are oriented along the same axis with respect to each other, here if you take 2 molecules of ethanol, there is nothing that binds them to have a certain orientation between them. They could be oriented at any different angle. That's largely because in solution state, these molecules tumble, meaning that they keep rotating about every possible axis. The translational, rotational, all these degrees of freedom allows them to sample all possible different orientations. Okay, so this time is important to ensure that we would be able to have an idea what will be the R2. Okay, so now in turn, what does tau C depend upon? If you assume your molecule is spherical, just for the sake of simplicity, spherical molecule, and applying the Stokes law of diffusion, tau C will work itself to be something like 4 pi over 3 times eta W RH the whole cube times kBT. Let's take each one of them at a given in a moment. This is a constant, right? You can imagine this comes up as the volume of whatever you're looking at, assume a sphere. 4 by 3 pi r cube, right? And in addition to that, the additional features that you have are eta W, which is the viscosity. And since we are working with water, we'll be talking about viscosity of water. And the RH cube is the radius of the molecule, but hydrated. Since we are talking more about biomolecular NMR, we are talking about hydration radius included in the spherical model. If you're trying to ask what happens for small molecules, you can imagine a solvent layer around the molecule, which will something be similar. No molecule is without solvent around it, right? Ordered set of molecules around it. Capital T is absolute temperature. Kb is Boltzmann's constant. So there are multiple factors that come in, meaning that the isotropic tumbling time depends on the size of the molecule, depends on the viscosity of the system and the temperature at which you're acquiring the data. This matters a lot. I'm going to discuss this a little bit. Please pay attention to understand. And if you have questions, feel free to ask, because this decides what solution state NMR is capable of performing. For instance, as the molecular size increases, do you see that the tau c increases? If tau c increases, R2 increases. And if R2 increases, T2 decreases. Okay? And therefore, as your molecule starts to become larger and larger, your transverse relaxation times go shorter and shorter. They go shorter and shorter, your uncertainty to measure a given resonance increases. This is a major outcome where in solution state NMR, there is a size limitation. You cannot measure NMR data for any size of molecule. As you start to increase the size of the molecule, the line widths increase because line widths are proportional to R2. Let me add one more component to it. Line widths are going to be given by R2 over pi, I think. Yeah, R2 over pi. It should be R2 star, but for now I'll write it as R2. R2 over pi. Delta nu full width at half height is given by R2 over pi. So as the molecular size increases, tau c increases. If tau c increases, R2 increases. If R2 increases, line width increases. So therefore, when you are measuring something for ethanol, you'll get very sharp lines to the tune of about 0.5 hertz, which I was talking to you about. But when you're trying to do the same thing for proteins or for nucleic acids or for maybe some of the larger carbohydrates, polysaccharides, you're going to have line widths in the tune of about 10 to 20 hertz. And at some point, the line width becomes so broad that your intensity goes down. Therefore, you cannot study very large molecules unless you do other tricks to reduce transverse relaxation time, which we'll keep out for the time being. Okay? So one of the major outcomes in understanding line width is that as the molecular size increases, your line width increases, and solution state NMR has a size limitation when it comes to measuring data. This is very important. On the other hand, solid state NMR doesn't suffer from it, but we'll keep it out for the discussion as we're not going into the detail of it. The other component that also severely affects is the viscosity of the medium. Generally, when you have a more viscous solution, the molecules cannot tumble a lot because there is resistance to tumbling due to viscosity. Therefore, as the molecules cannot reorient itself to every possible direction that fast, the tau c increases. Therefore, when you're trying to measure NMR spectrum in a viscous medium, lines are going to be broad again. You may try to take ethanol in, say, water and measure its NMR spectrum, or neat ethanol for that matter, which is very less in viscosity. On the other hand, you can take ethanol maybe in a condition such that you put it in glycerol or something, where ethanol will still be present, but glycerol's viscosity is high, due to which ethanol cannot reorient itself. You will see the lines are broader. I'll try to highlight the same thing in context of biomolecules in a moment, but please remember, as viscosity increases, tau c increases, therefore R2 increases, therefore line widths increase. Next component that comes up is temperature, and remember temperature is in the denominator. Therefore, you benefit by increasing temperature, meaning that as you increase absolute temperature, your viscosity reduces. Sorry, that's a different component. As the absolute temperature increases, the tau c reduces inversely. And therefore, many people at times measure data at 37 degrees, which also happens to be body temperature for biomolecules, because that helps in reducing tau c, right? Indirectly, which I outed without my knowledge, is that viscosity is also dependent on temperature. You know very well, as you increase temperature, viscosity also reduces. So getting NMR spectrum at higher temperature is many times preferred when you're not able to get well-resolved lines at lower temperature because of two reasons, meaning that temperature is inversely proportional to tau c, and most importantly, viscosity is also inversely proportional to absolute temperature. So if you increase temperature, there is a two-factor difference that comes up where the reduction in viscosity and increase in temperature allows for tau c to decrease further, making lines sharper. Now, the reason why I'm highlighting this so much is because there are times where some of your exchangeable protons, which is like hydroxyl proton or an amino proton in a protein in the backbone or an amino proton in nucleic acids, might be broad. And why is it broad? Maybe because chemical exchange happens. What is chemical exchange? Where you have a OH from your system and you have water molecule. Remember, this H can happily be exchanged, chemically exchanged. Therefore, when you're making a measurement, the same proton that was in water molecule now is in your peptide backbone. So therefore, that same proton during a measurement sees different chemical shifts. This results in also transverse relaxation, making the lines broader, because the proton doesn't know whether it's chemical shift at 5 ppm or at say 8 ppm, and keeps exchanging as a function of time. The line width also depends on the exchange rate, which we will see in a moment. And in such cases, it is beneficial to minimize the exchange rate because it's a kinetic process. You might want to reduce the kinetic process by reducing temperature. Because the exchange process is a chemical process. Chemical processes have an activation energy, and you know that with a given activation energy, if you reduce the temperature, the rate constant reduces. Therefore, you may be tempted to reduce the temperature also to make a measurement, right? But be aware, when you reduce the temperature, the viscosity of water increases kind of exponentially, okay? And therefore, the reduction in temperature also increases tau c because water is more viscous at lower temperatures. And also, the thermal energy available for your molecule is less, where it cannot reorient as fast as it was. Okay? So therefore, there are places where you have to measure in viscous medium. There are conditions where you have to measure at low temperature or high temperature. But whenever you're setting up experiments of that sort, please have this dependence in mind so that you know what is practically feasible and what is not. Okay, and importantly, you slowly realize that you will also be doing experiments in D2O, where you need to add deuterated solvent to your system, in which case the viscosity of D2O versus H2O is quite different. And yet again, remember, you're going to be adding salts in form of buffer to your entire solution, which also changes viscosity. All right, so there are multiple factors that get in that alters the properties of the solution, which in turn alters the property of the spectrum that you're trying to get out. Any questions from anyone? Yes. We don't want a molecule to tumble. The molecule automatically tumbles. The molecule has a thermal energy, and therefore it once again reorients every possible way at a given temperature. This is given because the rotational degrees of freedom has energy levels that are rather closely spaced, and therefore the thermal energy is enough for reorientation of the molecules. It's like trying to ask you, if you are in your room sitting, just wanting to relax, why do you walk around in your room? Do you do that at times? You don't? I do, for the sake of argument, right? Then you could ask, you wanted to relax, why are you walking? Some people get relaxation while you walk. That's largely because you have energy that you have to expend. There are people who keep moving their legs when they're sitting, right? There are people who keep on pushing their pen's cap So these are all energy that's available, and therefore you're going to sample states, although these are not important states to sample. So therefore tumbling happens automatically. It's not what we want to happen. On the other hand, for solid state, nothing such happens. The molecule, let's assume a single crystal to make your life simple. All the molecules are oriented in literally the same axis, at a given axis. There the tumbling doesn't happen. There the lines are broader. Instead of getting a single line like this, instead of getting a single line like this in a solid state NMR experiment, you'll get something called a powder pattern. Okay, you get a large range of frequencies due to some reasons. Okay, yeah.
Does the tumbling have any effect in the T2?
Yes, it does. That's what I was explaining for the last 10 minutes. Please listen to the lecture again. Okay, R2 is proportional to R2 is proportional to tau c, and I was explaining how does tau c affect. If tau c affects, R2 gets affected, R2 gets affected, T2 gets affected. Sure, no problem. Okay, so this is something where I had made a mistake in the previous class. We were talking about the tensor, which I wrote in terms which I would like to correct right now, where the chemical shift is a three-dimensional parameter. It need not be isotropic all the time. Since in solution state NMR, our molecule tumbles in every possible orientation, we will not find the anisotropy. So therefore, we will only find the isotropic component, which is the average of the trace. Trace is nothing but the sum of diagonal elements in the matrix. But now, for the other parameters to be measured, you need to do something called a principal axis system transformation. Don't worry about what it means if you don't understand. You can always diagonalize a 3x3 matrix. You can always start with a 3x3 matrix and diagonalize it such that only the diagonal components exist, such that you arrange them in sigma 11 greater than sigma 22 greater than sigma 33, which we call as something called a principal axis system. For now, let's not worry about this, where you can define anisotropy as sigma 11 minus sigma 22 plus sigma 33 by 2, and as asymmetry as 3 by 2 times sigma 22 minus sigma 33 by delta sigma. Why am I defining this? Is because last class I said a few things about anisotropy, and I think I defined anisotropy wrong. This is the correct definition of anisotropy, where it looks at the maximum component and looks at the orthogonal components, average of it, and difference between whatever is the major component and the average of the other two components. This gives you something called chemical shift anisotropy. The larger the chemical shift anisotropy, that indicates the electron cloud around the spin is more anisotropic. And therefore, you will have differences as you measure chemical shift from different axes. So if you get a solid state NMR spectrum, you're going to get something like this. Therefore, how do you get high resolution solid state NMR spectrum? We'll keep that discussion aside. You have to spin the sample at something called the magic angle so as to make sure lines get resolved. You mimic tumbling for solid state samples by spinning the sample with respect to the magnetic field. And therefore, you can go close to what you get in solution state by spinning faster and faster. Okay, so this is commonly referred to as magic angle spinning NMR, which you will learn a lot more when you learn solid state NMR. But this is where we will leave this in this course. Okay, hopefully you guys have understood how the magnetization comes up, and from there, how do we extract the information? And then from the extracted information, what all spectral features exist, especially chemical shifts and line widths, and how does line width get affected by various parameters? And at the same time, chemical shift also is complicated, but luckily solution state gives you only one. to make life easier. And importantly, the chemical shift anisotropy is also a reason for relaxation. Basically, the loss of phase coherence also happens when the spin sees different magnetic fields around itself. The spin relaxation has multiple components. There's something called a dipolar component. There's something called a chemical shift anisotropy component. Chemical shift anisotropy component arises due to this difference. Okay. I see that Deeptanu has raised his hand. Please go ahead, unmute yourself and speak up.
So what are delta sigma and eta called?
Okay, let me write it down. Chemical shift anisotropy. That is delta sigma. Eta is an asymmetry parameter. Yet again, if you understand the matrices reasonably well, when you arrange them in decreasing order, the isotropic component is the trace divided by 3. The reason why I didn't write it as 1, 1, 2, 2, 3, 3 right now is largely because if you understand matrix diagonalization, when you diagonalize a matrix, the trace will not change. Trace is invariant with respect to diagonalization. And importantly, the determinant of the matrix also remains invariant. And therefore, in a diagonalized matrix system, the product of the diagonal components would be the determinant of this matrix. So therefore, if you arrange them in decreasing order, what you're going to have is that this is going to be the major component. You could have cases, let's say it's a totally symmetric system. Let's take an example of methane molecule, where the proton has a very symmetric distribution of electron cloud around it, more or less. You're going to have these components to be 0, where you measure an isotropic component itself from this entire shielding tensor. But on the other hand, when you're taking an example such that, let's say HF, just for the sake of it, where the fluorine ends up taking quite a bit of the electron cloud towards itself, the anisotropy is going to be significant, where in addition to having one major component, it's going to have the other two components as well. The deviation of the other two components from the major components defines something called asymmetry, or rather anisotropy, sorry. Okay. And at the same time, difference between the deviations defines what is called asymmetry. You could have cases where sigma 2 is equal to sigma 3, meaning that these two are equally, the magnitude is equal in nature. And therefore, you could have systems like that, where the anisotropy goes that way. It all depends upon the electron cloud around the spin. And take metals, for example, you could have very weird distributions of what you have here. So those are the names for delta sigma and eta. Any other questions, Deeptanu?
No, sir.
Anybody else? Okay. Any questions from here? Okay, now let's get into the details of many questions we have had. I'm happy that people are asking questions. How does an RF pulse affect a transition and whatnot? Yes, a question from here. Cross terms are not 0 because of symmetry. Whenever you are making a measurement in solid state NMR, you need not be aligned in the principal axis system to make a measurement. Okay, when you make a measurement, you will probably get all the off diagonal terms. But you would, in order to define something, see, remember, therefore, every measurement would change these values. So then how would you define asymmetry or anisotropy? You're better off defining it in terms that will never be changing. So for a 3x3 matrix, in order to make sure nothing changes, if you can diagonalize it, your life becomes better. Okay, and the diagonalized system will only change your coordinate system from where you started to something else. The some other coordinate system where the components of the shielding tensor are only diagonal is called the principal axis system. Okay. So now what we will look at is how does the magnetization that we have generated change as a function of time. This is very important. This is where we are going to be spending the remaining of this week. So far, we have not seen the influence of it in mathematical terms. We just did it in qualitative terms. What do I mean by this? We did not have a magnetic field that changes as a function of time. We only had a constant magnetic field B naught, and we said it's along K. I did not define how the RF pulse ended up working. I just told you the M naught that you had to start with and the B naught that you had were collinear, therefore the cross product results in 0 and therefore you cannot measure it. And I pushed M naught wantedly to something like J with the B naught being along K such that the J cross K is non-zero and therefore we end up measuring, right? Now we'll go into further detail of understanding how this expression works. These are called the block equations. This is going to be very important to understand, and it's named after Felix Bloch. Felix Bloch and I forget what Purcell. Bloch and Purcell were the first two people who showed magnetic induction is possible in 1949 or so. Okay, and for which they won the first Nobel Prize in physics. And from there on, people thought NMR, that is nuclear induction, that's what it was called, nuclear magnetic induction, is a technique that's only useful to measure gamma, which is gyromagnetic ratio. Because they threw water in, they got a single signal, they were able to define gamma for water. Interestingly, when other molecules are put in a magnetic field, they got more lines than one, for instance, paraffin wax. So they were trying to use NMR as a single point measurement, like a melting temperature or boiling point, right? They were very naive. They did not know what was chemical shift at that point of time. So when they ended up throwing paraffin wax, I think they got at multiple signals, or maybe that gave still one signal. The landmark measurement was made when ethanol molecule was put in a magnet to measure NMR spectrum. It gave 3 lines, which is also why I keep using the same molecule, because it has a lot of legacy behind where NMR is today. Because they put in ethanol, they got 3 lines. So the immediate question that came up, which line should we use to measure gamma? Right? Should we measure 3 and average it? But then the best part about scientists is you start to wonder, why did you get 3 lines? Is it a mistake of your measurement, or is it an intrinsic property? If it's a mistake of your measurement, you recalibrate, do your experiment again to make sure you get it right. But in spite of doing every possible right way of setup, you still get an anomaly such as this, which was not observed until then. Then you try to ask what is the phenomenon that leads to something like this. That's essentially how chemical shifts were observed. And that's when people start to understand NMR has a much larger potential. This was during mid-50s, if I'm not wrong. NMR has a much larger potential in catering towards chemical characterization. Okay. Even then, NMR was dealt with in a continuous wave mode, which we will not be discussing in this course. What is a continuous wave mode? This is the way you run your UV visible spectrophotometry, where you sweep a field from lower energy to higher energy. And when you sweep it, wherever an absorbance happens, you call it a chemical shift. Okay, so that's how NMR was measured in, say, 50s, 60s. Until late 60s or later than mid 60s, where Fourier transform based NMR was established. Then you may ask, okay, when life was very simple, you just swept the field, you could get the spectrum. Why are we complicating our life with something more mathematical than whatever is required? That's largely because you have learned that NMR is an intrinsically insensitive technique. Therefore, a single sweep is not enough. You got to sweep the same thing again and again to do something called signal averaging, meaning that if your signal is not good, you repeat the same experiment again and again, add up the outcome. Since it's a linear technique, you could add it and still get the same information. So when you start repeating the same experiment in a sweep-based method, the experiment takes a very long time to finish. There are papers that show a single scan of sweep, continuous wave NMR experiment, and a single scan Fourier transform experiment takes the same amount of time. But when you have to repeat it again and again, the Fourier transform based method is much better than the continuous wave NMR. Okay, so therefore we will only be discussing Fourier transform NMR in this course because only that exists today. Still, EPR is significantly done in continuous wave mode. So if you want to see a continuous wave NMR equivalent experiment, you can take a look at how EPR spectra are acquired. It is just a single scan that they end up getting, where you just scan the field and you get a resonance and you're done. Okay. So with that being the premise, let's go into understanding how would we end up moving M0 to the transverse plane. You realize that at that moment, I said you apply an RF field that somehow negates the B0 effect and allows for the effective magnetic field to be existing along the x-axis that moves the Z towards the Z axis oriented bulk magnetization to the y-axis. That's how we ended up measuring it, right? So right now, in order to understand this, we have to move ourselves to a frame called a rotating frame. From now on, I'm going to drop the M of t. The magnetization is a function of time and the magnetic field is also a function of time. But I'm not going to keep writing it for the sake of brevity. So right now, what we are going to do, we are going to go into a new frame of reference where the frame of reference also keeps moving. I'll tell you why this has to be dealt with. But let's assume the angular frequency of such a frame of reference is omega. Okay, we choose omega such that we are in a frame of reference which keeps moving as a function of time with respect to the lab frame. So therefore, what is going to happen? dm over dt in the lab frame. In addition to that, you are going to have the magnetization that changes in the frame of reference you're trying to talk about. What we are trying to say? From the rotating frame, if you're trying to ask, how does the magnetization change as a function of time? Angular frequency of rotating frame. Okay. Now to answer your question, why should we go to such a frame? Remember, we are talking about bulk magnetization, but the important aspect that you guys have to remember, the bulk magnetization is a result of nuclear spins precessing about B0. So if you want your disturbance to effectively interact with such spins which are precessing as a function of time, let's say at 500 megahertz, do you realize you should also make sure the disturbance precesses at that field? An example that I always give in this course to make people understand this is that let's imagine a mom has to feed a baby who's playing in a merry-go-round. Let's say the merry-go-round is stationary, the mom will be able to easily feed the baby, right? Therefore, effectively get the job done. But on the other hand, let's say the merry-go-round starts to move. Yeah, and the mom tries to feed by being stationary. Will the mom succeed? Yes, but very, very low in probability. Okay, out of 100 times the mom tries to feed, maybe 1 or 2 times they'll succeed just by chance. Right? The baby might just be there and therefore the baby may take the food. But realize that's going to be extremely inefficient. So in order to do this, what should the mom do? Run with the merry-go-round at the same frequency. So similarly, the RF field that you're trying to apply also has to have a frequency component such that it goes with the spins so as to affect the spins to bunch them up together. This is the work done from the RF field that you're trying to achieve. What is going to do as it processes, remember, as the RF field processes, it'll try to homogenize the XY random phase that existed becomes coherent with an effect of RF pulse that it achieves by making sure it's also processing with the spins. This is a very, very important component of NMR. This is the resonance part of NMR. This is the R part of NMR. This is what makes NMR different from fluorescence spectroscopy or UV visible. Nowadays, IR is also done in the pulsed way, which has its similar components, but overall, this is what is distinguishing a resonance technique versus an excitation absorbance technique. Yeah. So where now, what we are going to do right now is to rewrite the dm over dt in the rotating frame. Why do you want to do it in the rotating frame? Because remember, B0 will always exist. You're never going to turn off B0. The precession with respect to B0 will always exist. So let's say we are going to the rotating frame in order to understand the effectiveness of the RF field to get the magnetization to non-longitudinal axis. In addition, to not look at the motion of magnetization with respect to B naught. Remember, we are talking about magnetic fields. Now we are going to talk about effective magnetic fields. When you're talking about effective magnetic fields, B naught will always exist. And therefore, the precision with respect to B naught will always keep creeping in the visualization that you're trying to do. Let's say I don't want to see the precision with respect to B naught because I know it always exists. Why should I look at it? So the rotating frame goes to a frame of reference such that the precision with respect to B naught will not be seen, provided you are on something called on resonance, which we'll see in a moment. Okay. So therefore, what is going to happen? This is going to be M cross gamma B plus M cross omega, which you can rewrite as M cross gamma B plus omega by gamma. Okay, so therefore, what has happened? Yeah, in the rotating frame as well, you have an equation that's very similar to what you started off with. The rate of change of magnetization is given by the cross product of the magnetization with respect to an effective magnetic field, because there's a proportionality constant to make sure units are taken care. And gamma is a constant for a given spin, right? It's still M cross B if you realize. Make sense? Here is where we define the Larmor precision frequency, which is why, although I said omega is gamma B naught, now you will see actually when you set omega to minus gamma B naught, then dm over dt in the rotating frame is 0. What do we mean by this? When you set the angular frequency to the Larmor precision frequency, I'm writing it in poor ways. Wait a moment. That's also. Okay. When you're having the precision frequency, when you have the rotating frame rotated about the z-axis, where the frame keeps rotating, where x and y keeps changing, but z-axis aligns with the lab frame. Right? Not as complicated as the principal axis system. This is very simple. You take an xyz right-handed coordinated system and you rotate above the z-axis. Okay, which once again makes sense. Your precision is also about the z-axis. So therefore, keeping z-axis as the reference makes total sense, right? When you set this, what's going to happen? This effective part at equilibrium goes to 0, which is where your magnetization remains same, irrespective of the lab frame or the rotating frame. Okay. Now we are going to pay more attention to detail on an effective frame when we are applying an RF pulse, because RF pulse is the light that allows you for disturbance to happen. So shall we cause the disturbance? So the disturbance is in the form of, let's say, BRF. Sorry, that's because only when you negate the component. So if you put omega to minus gamma B naught, magnitude of it, omega naught is minus gamma B naught, you realize this factor goes to 0 at equilibrium, of course. Okay, because this will be B naught K, but that's why I wrote the K to make sure you understand there is a vector. We cannot just blindly write a vector without any notation. Therefore, I wrote K cap. Okay, the minus comes from the fact that you are rotating with respect to it so that you negate the effects of it and you don't see that happening anymore. Now, if you take the cone of alpha spins and beta spins in the rotating frame, they don't move at all. They are stationary. Do you understand that? On the other hand, the cone also moves in the lab frame and you don't want to see that movement. Therefore, you go to the rotating frame. Now, let's take a look at the electromagnetic radiation, which is the light that you're applying to the sample, because that's what is spectroscopy, right? Interaction of light with matter. All the matter is embedded into M naught. So we'll keep that aside. We have seen the matter for quite a bit. Now let's take a look at light. Light is generally an electromagnetic radiation which has a given amplitude with a sinusoidal component to it. Amplitude, the sinusoidal wave, right? Because you're going to have a, that's how magnetic, electromagnetic fields work. You have a magnetic and electric components that are orthogonal to one another. Since you're only dealing with nuclear magnetic resonance or spin-half systems, do not worry about the electric component. You're going to just not worry about the electric component and only look at the magnetic component. The magnetic component is going to be given by an amplitude followed by a sinusoidal wave applied at a certain axis. You can apply the pulse whichever axis you prefer to. Given that your magnetization is along Z, there is no point in applying the pulse also along Z, in which case it will not affect a change. You already have a field along Z, which is B naught. It cannot change M naught. You cannot measure it. So you're better off applying a pulse in the transverse plane. Okay? And right now in the transverse plane, what has happened here is to set it along the x-axis at an angle of phi, a phase angle of phi. So what do I mean by this? Right now I'm going to draw what is being done only with respect to the magnetic fields. X, Y, and Z, and then you're applying an RF pulse, which is BRF, which is also an actor, which subtends an angle phi with respect to X, has projection of the necessary components. What is going to be the projection here? This is going to be, okay, let me write the projections in one moment, because that's going to change after we write it. Does that make sense? Of course, you can always set phi to 0. That's an X phase pulse. You can always set phi to Y, where phi therefore becomes pi by 2. You can always set the pulse along minus X, in which case phi is pi. You can set the pulse along minus Y, in which case phi is minus pi by 2 or 3 pi by 2, right? You can set the phase as 45 degrees, pi by 4 as well. You can set the pulse anywhere in the XY plane, provided it serves a certain purpose. And our purpose is get it to the transverse plane. For 1D NMR, you can set the pulse along anywhere in the transverse plane, you'll be able to measure whatever you want. Okay, but as you go in higher dimensionality, you want the pulse and the pulse phase to be played along with, so as to make sure the outcome that you're preparing it for, you'll be able to achieve. That we'll see for the quantum component. All that we have to understand right now, bulk magnetization exists and you have the power to disturb it. And when you disturb it, you have the power over where it's going to come up so that you can end up measuring it. Make sense? And in order to do that, you end up getting the electromagnetic radiation, which has a form such as this, which has 2b1 cos omega RF t plus phi. And here is where the omega RF is the frequency at which you're applying the pulse, right? The angular frequency at which you're applying the pulse. Yet again, the pulse frequency should match omega naught, at least be close enough to omega naught to make a difference. This is exactly where the mom is also running at the speed of the merry-go-round. Then you would ask, why did we go to the rotating frame? The rotating frame is one where the entire earth rotates such that although the merry-go-round and the mom are rotating and running, they'll appear stationary. That's our visualization. Okay, rotating frame that you're trying to look at is more of a visual perception or visualization to negate the effect of precession of M with respect to B naught. On the other hand, the omega RF that you're trying to do is actually what is doing the job. The mom running is what is actually doing the job, not the earth rotating. Right? Earth doesn't rotate. But then if you go to the frame of reference, say you have a camera, right? And that is the lab frame, where you stand and take the picture. What's going to happen? Merry-go-round is going to keep going. The child is going to keep moving. The mom is also going to keep moving. Therefore, you don't capture the mom or the child effectively on whether the mom is able to feed the baby. You know that they're both running together, but you do not know what's happening, right? On the other hand, as a camera person yourself, you run along with them in the same frequency. You'll be able to see what's happening. And at that moment, the merry-go-round, the kid, and the mom will appear stationary. So the reason why we go to the rotating frame is to negate visualization of M precession with respect to B naught. The reason why you have this is the reason why you have the resonance component in NMR, where the field that is applied is on resonance or close enough to resonance to make sure the spins which are processing are able to feel the experience the field that you're applying. Else they'll be ineffective. Let's say this component did not exist. Your pulse will not affect any changes of population, will not create any coherence, phase coherence. It'll completely fail in it. I think this was your question a few classes back. How does it do it? It does it by also running along with itself. Okay, and okay, now let's continue further. So you had something like BRF is 2B1 cos omega RF T plus phi times I cap. Now, for the sake of simplicity, I'm going to divide this into two components. What are the two components? I'm going to write B1 cos omega RF T plus phi I cap plus sine omega RF T plus phi j cap plus B1 cos omega RF T plus phi I cap minus sine omega RF T plus phi j cap. What have we done? All we did was to add and subtract a sine component to it. Okay, it still remains to B1 cos omega RF T plus phi I cap. The reason why this was done is because now you will be able to understand linearly polarized light is now decomposed into two circularly polarized light. What does this mean? The cos part, cos plus sine part, let's assume it goes in the clockwise direction. For people who are not following it, let's draw a two-dimensional graph where you have something like this and you have a phi component. If you drop the projection, this is going to be B1 cos phi. If you drop this projection, it's going to be B1 sin phi. And the phi keeps going in the counterclockwise direction, right? So, sorry. So let's say this keeps going this way. Yeah. So if you take at any point, let's say this on a projection, you get B1 cos phi plus B1 sin phi. It's a cos phi comma sin phi kind of component is what you're saying there. All right. On the other hand, if you're going the other way, it's going to be B1 cos phi minus B1 sin phi. So basically what you've done is that you have a linearly polarized light. You're not decomposed into right circularly polarized light and left circularly polarized light. So with this, let's stop the class and we'll continue it on Thursday. Please go over this in the Kamina book. Okay.